Okay, I've decided to split up the videos into two videos. So for the first video, I'm just going to cover question one, and for the second video, I'll cover the Kaggle data set. So for question one, we were given a list of independent and dependent variables, and we were asked to pick one of each and to do some analysis of it. So I ended up choosing y1 as my dependent variable and x3 as my independent variable. For question A, we were asked to find the conditional probability where x is greater than x, given that y is greater than y. To find the conditional probability, you have to find the probability of x intersect y divided by the probability of y. So to find the intersection of x and y, it's a simple filter programmatically. So the probability of x intersect y was 0.2, and the probability of y is 0.75. So we have our answer of 0.2667. I took an extra step, and we actually had to do this later on anyway, but then asked the question of, are they independent? And for them to be independent, the probability of x given x would have to equal the probability of x given the probability of y given y. So that would mean that the probability of y given y should have no effect on the probability of x given x. And when I plug it in here, you actually see that it's false, that they are in fact dependent on each other. For question B, it was just a simple question of find the probability of x given x and the probability of y given y, which is just 0.25 times 0.2, which equals 0.15. Now for question C, we were pretty much asked to find the complement of question A. So in question A, it was a less than filter, or it was a greater than filter, and in this one, it's a less than filter. So it's the same work, same math as done in question A, plugged into question C, and you would think we would get our complement. And so the complement should equal 0.73 something. But in reality, we actually got an answer of 0.6667. And the reason for that was because this doesn't account for that in this array, there's examples where x is actually equal to x. So the probability where x is equal to x was actually 0.06667. So when we add the probability x is equal to x plus the probability where x is greater than x and the probability where x is less than x, we get a sum of 1, which it shows here. Does 1 equal all these things? Now for the next question, we were asked to find a table of counts. And using the table of counts, I was able to confirm part of my questions, part of the first questions for question A. The reason I couldn't confirm it all was that the table of counts actually had to do with greater than or equal. It had to do with, because of the fact that we don't have greater than or equal, the confirming the part C wouldn't work. So to confirm part A, well, here's our table. And we say, okay, well, we have to find where is y greater than y. So y is greater than y in this row. And where is x greater than x? Well, that equals 4. So now we know that our conditional probability would be 4 out of 15, which equals 0.2667, which was our answer for the first problem. Moving on, we were asked to kind of refilter the data set in a different way and see if that filtering created a independence. Now, I think the idea of this question was to show that while our probability that we discover by using our Bayes theorem would show us that the variables were actually dependent upon each other, that when we plug that into a chi-square test, it doesn't always show the same thing. So to start here, we have, what is the probability A given B so to prove that independence, we have to say that the probability of A given B is equal to the probability of A. So in other words, the probability of B should have no effect on, once B has occurred, it should have no effect on the probability of A occurring. So once again, we have the probability of A intersect B divided by B. And we found that this was equal to 0.667, and we found that the probability of A was equal to 0.65. So if we were to use this, strictly speaking, we would say that this condition is not met, therefore these variables are dependent upon each other. But when we plug it into the chi-square test, which I do here, I created a table, and then from the table, I created the expected values from what you would from over here. We see that we get a chi-square score of 8.2, which turns out to give us a p-value of 0.2381 when we plug it into the chi-square table. So what the test is determining is determining independence. So the assumption is independence. The null hypothesis is independence. So we fail to reject the null when we have a p-value of 0.23. Therefore, the variables according to the chi-square test are independent, which is actually contrary to what our math would have told us. But we should probably assume that our math, if we look back, 0.667 and 0.65 are relatively close to each other, and there isn't many samples in this data frame. So through chance, it probably makes more sense that the chi-square test is correct and that our assumption above before it was wrong, and that these variables are actually, in fact, independent.